Okay, so welcome back, and today we're going to be looking at defining oxidants and reductants. So this can get a little bit confusing because of the terminology sounds very similar. You've just got to be careful and pay attention to what's going on with the electrons, and we'll look at ways to be able to see what's happening there. So in this video, we're going to be looking at defining the terms oxidant and reductant. So these are things where you do need to know a definition for. Being able to identify oxidants and reductants in a redox equation. Write simple half equations for redox reactions. So we need to be able to write half equations in order to balance full equations for redox. Identify the half equations as either oxidation or reduction processes, and then we will look at writing complete redox equations for simple reactions at this stage. So you may remember back to very early on in our studies in chemistry where we did the prac where we took magnesium ribbon, we heated it up and we formed magnesium oxide. This is actually an example of a redox reaction, okay? And we have oxidation and reduction occurring simultaneously. The overall reaction that we wrote is this one here. This magnesium solid plus oxygen gas gives us 2 magnesium oxide solid. Remember, this is the formation of an ionic product. So of course, as we said before, this will be a redox process. We can actually look at what's happening at the atomic level in this case, in that we know that the magnesium is giving up 2 electrons to each oxygen to form this ionic bond. So we can say that because the magnesium solid is losing electrons, okay, so magnesium is losing electrons. If we think back to our oil rig mnemonic, then oxidation is lost, so it is being oxidized. Because it is being oxidized, what it is doing is forcing its electrons onto the oxygen. So by giving the oxygen electrons, it's facilitating the oxygen to be reduced. So we call magnesium the reductant because it is allowing oxygen to be reduced by giving it its electrons. And because reduction is gain, okay, so oxygen is reduced, magnesium is oxidized, but we call magnesium the reductant. And because oxygen is facilitating the oxidation of magnesium, we call it the oxidant. So we can actually pull this out into 2 half equations. One that shows us what's happening with the oxidation process and one that shows us what's happening with the reduction process. Okay, so each one of these are called half equations. And when we deal with redox processes, we tend to deal with net ionic balanced half equations. So for the oxidation reaction, we said magnesium was being oxidized. So magnesium solid goes to magnesium 2+, it's still solid, plus 2 electrons. Okay, so the loss of electrons means it's been oxidized. Reduction, oxygen gas plus 4 electrons gives us 2 oxide anions, showing that the oxygen molecule has been reduced. Now, if we think about it, with oxygen being lost, when we lose anything out of a chemical reaction, it's essentially the same as it being produced. And if we see this here, we see the electrons are on the product side, which means that they are being lost from the magnesium and produced as something on the other side. So anytime we have an oxidation reaction, okay, the electrons are on the right. Okay, whereas a reduction reaction, we get this addition of electrons in, so they're being added in, so they're acting as a reductant, so therefore we get the electrons on the left-hand side. Okay, so we get this reactant kind of process every time for reduction. One way you can remember this is to change our oil rig mnemonic into Euler and Rigel. It's up to you, but oil rig, oxidation is loss, reduction is gain. When we lose electrons, they're on the right-hand side. When we gain electrons, they're on the left-hand side. So the terminology here, because magnesium is the electron donor, it allows oxygen to be reduced, so we call it the reducing agent or the reductant. The reducing agent, okay, or the reductant always undergoes oxidation, and the oxidizing agent always undergoes reduction. And we can always find what we call redox pairs, like we did with acids and bases in terms of conjugate pairs. We can find a redox conjugate pair, the magnesium with its electrons, the magnesium after losing its electrons, the oxygen with a normal number of electrons, the oxygen having gained electrons there. So when we come to write overall redox equations, what we need to do is we need to split both our processes, one oxidation process, one reduction process, balance each half equation, okay? Then we add the two half equations together to determine the overall redox reaction. The key thing that we need to do here is remember that our electrons must balance, which means we have to have the same number of electrons on each side, because essentially we want to be able to cancel them out. So in the case of our magnesium one, where we had 2 electrons being produced, we'd also have to have 2 electrons being used so that we can cancel them out on either side of the equation. So both equations, okay, in order for half and overall equations, we need to remember the law of conservation in mass. So atoms are conserved in all chemical reactions. If it turns up on one side, it has to turn up on the other. Okay, and then this idea that charge is conserved in chemical reactions as well, that the electrons on one side must equal the electrons on the other side of the reaction. So when they're added together, we can never have electrons just hanging out on their own, because that's not how we find them. They always need to be paired up with an atom, so we can't just leave electrons hanging out. If they don't cancel out, then something's gone wrong, and you probably need to multiply one of the half equations. So let's have a look. If we look at this reaction here, we're talking about a strip of zinc metal is placed into a copper 2 nitrate solution and left overnight. The blue color of the copper solution fades and a deposit of dark reddish copper metal forms initially on the zinc surface. So this is a metal displacement reaction, and we've seen a lot of these so far in our study. Okay, so a metal displacement reaction. And it initially forms on the zinc surface. The zinc strip dissolves slowly, and first of all, we're being asked if this is a redox reaction. And the answer is it is, as you probably expect. And it's because what we have here is we know that the zinc strip, so zinc solid, is disappearing. It's oxidizing. It's corroding away. So it's turning into zinc 2+ aqueous. Okay, and we can see here that then the copper, we know copper 2+ is blue in solution. We have copper nitrate, which is essentially a copper 2+ solution. And we're getting solid copper forming on the ground here and in the bottom of the flask and on the surface of the zinc, which means that it must be turning into copper solid. Now, looking at these two half equations of what's happening to the zinc and what's happening to the copper, you should be able to determine here that the zinc solid is being oxidized because it goes from being 0 charge to +2, okay, which means it must have lost some electrons, so it's lost 2 electrons. Okay, and the copper here is going from copper 2+ to copper solid, which it must have done by gaining 2 electrons. So in this case, we can see now my electrons are on the left, so this one is being reduced. So this is the reduction half equation. So when we bring them together, I can just add the 2 equations together like doing simultaneous equations, and I get Zn solid plus Cu2+, and plus 2 electrons goes to Cu solid plus Zn2+ aqueous plus 2 electrons. And just like if we have 2 things on each side of a equal sign, I can cross out my 2 electrons, which leaves me with Zn solid plus copper 2+ aqueous goes to copper solid plus zinc 2+ aqueous. Okay, so let's have a look at a few more of these. With this question, we have again the situation where we're placing a piece of metal into a solution of a metal salt. So in this case, we have nickel. being placed into a silver nitrate solution, and we're told that the nickel dissolves and a deposit of silver forms. We're asked to write half equations and an overall ionic equation for the reaction. Remembering with the ionic equations, we ignore spectator ions. And then we're asked to identify the oxidizing and reducing agents. I want you to pause the video, have a go at this, and then we'll go through the solution. Hopefully you've had a go at this yourself, and this is what your answer looks like. If we think about the situation that was described, we were told that we have a solution here which contains silver nitrate, which would be AgNO3, which is essentially a solution of Ag plus ions and NO3 minus ions. And we're told that when we place a piece of nickel in here, so nickel solid, that a deposit was formed and that the nickel started to corrode away. So what this is telling us is that all these hints are pointing us towards a metal displacement reaction, that the nickel is turning into nickel 2 plus and the silver is forming nickel solid, silver solid. So if we write this out for our first half equation, we can see that we would have nickel solid is going to nickel 2 plus aqueous, because this is going to be the soluble ion of nickel, plus 2 electrons. And then the silver, which started off as Ag plus, well, for it to be silver solid, it must have gone to Ag solid, which is uncharged. So we've had silver plus an electron gives us silver solid. Because this one is generating electrons on the right-hand side, and we have nickel going from a neutral atom to a 2 plus, it's lost 2 electrons, so we can say this is oxidation. In the case of the silver is going from a plus charge state to a 0 charge state, so it must have gotten 1 negative charge from somewhere, and that's going to be an electron. So this is reduction overall. So if we write the overall equation, we just want to combine these two, but we can see that I have 2 electrons on the right-hand side and only 1 electron on the left-hand side, which means that I'll need to multiply this equation by 2 to give me the right number of electrons to cancel out. So when I do this, I end up with nickel solid plus now 2 Ag plus, because this would give me 2 electrons, and then these can cancel out, which will leave me with nickel 2 plus from my top equation, and then 2 Ag solid, remembering to put in all my equations and states for my equation. If we think about oxidizing and reducing agents now, in oxidation, it was the nickel solid that was oxidized, which makes it our reducing agent. And then the Ag plus, we're always the species that it's happening to, the Ag plus that was reduced, which makes it our oxidizing agent. Here's another one for you to try. I want you to give this one a try on your own, and then I will upload the solutions onto the PowerPoint on Schoology and check your answers before we go through them in class. Okay, hopefully you had a good success with the last question. This is just looking at a multiple choice question where it's asking us to rewrite each of the, sorry, not a multiple choice, just a multi-part question. And it's asking to rewrite each of the following 2 half equations, indicating which represents oxidation and which represents reduction. Okay, so we need to take these full equations and now pull out the half equations from it, which means that we're going to be looking for our redox pairs in order to write our half equation. So let's do the first one together. If we look at zinc plus 2H plus goes to Zn2 plus and H2. First thing I want to identify my redox pairs. I have zinc solid and Zn2 plus, because these are the 2 things where zinc is linked and we can't turn things into different atoms. And then H plus and H2. So in this case, sorry about the bell, in this case, our first equation that we could pull out is Zn solid goes to Zn2 plus. Okay, so Zn2 plus, which we see here. So Zn solid goes to Zn2 plus. And then because this is more positive on this side, we're going to add our 2 electrons over here. And then H plus 2 electrons is going to give us H2. So 2H plus here, so we can end up with a full hydrogen molecule over here. Same again for number B, we have magnesium and oxygen reacting to form magnesium oxide, which is the one that we did in class.
And we can say that the magnesium solid goes to magnesium 2+ in this ionic compound. Be careful here because remember it is a solid, it's not aqueous in this one, we just burnt the metallic ribbon to form the solid. And then oxygen going to O2- and balancing our charge on this one. Clearly our one up here is incomplete with B because we need to have the 2 electrons on the left-hand side here as well. Just as before, pause the video and complete C and D and then check the answers from the PowerPoint that's uploaded onto Schoology. Here's another question, same thing. I want you to complete these questions and then bring your worked answers to class for the next lesson. Okay, so hopefully you've had a bit of practice and you're feeling pretty confident in defining our oxidant and reductant terminology, identifying oxidants and reductants in a redox equation, having a bit of practice with our half equations and writing full equations. Of course, as always, we will have a bit more practice of this in class. So read over your notes, have a look at your textbook and start doing those minimum questions so that we can get on top of this and then move on to more complex redox equations.